Hello, friends, and welcome back for part two of Global Hack Week data, what's that house worth? I've decided we need to differentiate because there's another machine learning track. So this is the what's that house worth track. Yes, Kalimba, always bringing in the Kalimba. Shamari, it's so good to see you here. Last time. Let's do our traditional beverage check. What is everybody drinking? I'm drinking some water out of a cup that they told me it was for single use and that it should be recycled. It's aluminum. But I just put it in the dishwasher and have continued to use it, and it is working. It is getting like a little interesting kind of patina. I don't know if you can. Oh, I'm really bad at like hiding my face. Oh, there you go. Interesting little patina, but it still holds water, so I think that's about as much as you can hope for a cup. But I am super psyched to be back. Yesterday was sort of our just generic intro to Python session, which it did, if you were there, it did get a lot nerdier, a lot faster than I expected, which was great. But even with that, intro to Python is just a pretty standard session that we do, and this time we kind of really get to dig into what makes this Global Hack Week different, which is of course the data. So I will, let's see, I will drop our check-in link because we always got to fill out that, and then we will walk through it in just a second, but here is the link to the Kaggle competition. That is kind of where all of our stuff lives. So if you missed yesterday, it's actually totally fine. As long as you know Python and you missed yesterday, you are doing great and don't need to even go back and watch it. You can if you want, but you don't have to. But if you don't know Python at all, then it would be a great entry point. I am so glad to hear that's. I actually didn't think about that as sort of the user experience, that you are, on another tab somewhere and the Kalimba sort of pulls you back, which is great. Oh my goodness, Dark Rules, I'm touched. Thank you so much. I enjoy doing MLH stuff, so I'm glad to hear that you are glad to see me, because I'm glad to see you. Cool. We are back at it. So today we are diving into our data. We're going to talk about like what a machine learning model is, and then we are going to do a little bit of feature engineering. And if you don't know what feature engineering is, we'll talk about that as well. We will also, of course, cover, or we'll go back and cover the leaderboard, actually some fun developments. There are some discussions, and somebody published a notebook, which is awesome. And so we'll cover all of that. And yeah, I'm generally looking forward to it. I guess sort of per custom, does anybody have any questions from yesterday or from looking at the data themselves recently? If there are any questions currently, I am happy to field them here and now. Okay, Bugbreaker did some math, gradient descent, and linear regression on the data set. We got some errors. Okay, well, I am. We are actually. I don't know if we'll get to linear regression today. If we don't, we will definitely get to linear regression tomorrow. But yeah, that's in it. We're doing machine learning. I love to see it. If you don't know what linear regression or gradient descent means, don't worry about it. It's fine. But we will talk about linear regression in a minute. Thank you for letting us know you'll be on a work call. We're psyched to have you when you come back, and we'll keep it chill until then. You can submit the notebook, yes. Okay, so this is actually a great question. I missed part of the last part of yesterday's session. Are we supposed to submit something at the end of this track? Yes. So to participate in this Kaggle competition, you will submit one of your notebooks. It could be one that you copied from me, but you will submit one of your notebooks to the competition. And I will cover how to do that in depth, I think both today and tomorrow and the last day. So you won't miss it if you're tuning in. We'll cover it several times. But yeah, there's just a submit button that you can click that sort of enters in your predictions into the competition. And when you do that, actually, excellent segue. When you do that, you will show up on our leaderboard, which we already have six submissions, which is incredible. I believe Reber Singh, I believe this is the one that that we did together. If not, you can correct me. But I believe this is the one that we did together. That if you just copied my submitting notebook, then this is the score you'd get. And then we see some people doing a little bit better. So remember, the score here is on average. How wrong was your prediction? I just realized that my head is kind of cutting this off, but I don't necessarily know. Yeah, it's fine. You can see the. I guess I can scroll. No, I can't scroll further down. So on average, this right here, a little bit hard to see, but on average, when you predicted the price of a house, you were $251,000 away from the right answer. So that's like a pretty bad, I mean, not bad. All these are good, right? We're learning, we're doing the thing. Whereas you come up, this is on average, the prediction was 60,000 away from the right answer. So that's like actually close. And then all the way up here, Salaziev, on average, when they predicted the price of a house, they were only $55,000 away from the actual true price it sold for. So that's suddenly $55,000. That's suddenly getting into the realm of like, maybe this is actually kind of a useful indicator, right? Depending on, what kinds of houses you're looking at. OMG, hello, Kaka Prague. It's good to see you. It's been more than a month, I think. So it definitely has, because I haven't been on stream in more than a month. But it is good to have you back. So that's our leaderboard. And so when you submit, you will show up here. We can do a quick recap. I guess we'll do a recap of Kaggle. So Kaggle is this platform where we can do machine learning competitions. So on this platform, you can learn how to build machine learning models, and you can also pit your model against somebody else's. So that's how we end up with this leaderboard. Is everybody has built their own little AI model, and they're competing on the leaderboard. If you go to the overview, you can just get all of our check-in links and have some general information about what we're doing here. The data tab, this is actually really where we're going to spend a decent chunk of time, because we're going to be doing a lot of our sort of exploring our data set today, which is really exciting. And then code is usually where you will start off. The sort of the easiest way to get going here is to copy the code that I am working on. So part 2 is what we're going to be tackling today. And if you click on exploring our data, you should have a button here that says copy and edit. And so then you can get a copy of all of the code that I'm working with today. As we go forward, you can kind of play around with it and follow along. In fact, I'll click that there. So if you click copy and edit, you should see a screen that looks a little bit like this. Oh, hello, Trishatomy. I don't know if that's actually how you pronounce your username. I want to say Trishatomy, but it's good to see you. It's been a while. Cool. So if you've never done anything on Kaggle or anything with a notebook before, this is kind of what we covered yesterday. But you have these little cells of code, and you can click the play button here, and it just runs the code just in that cell, which is the sort of easy way to iterate and play with little bits of code. And if you want to come and change something, you don't have to run all your code again. You can just change that little bit and rerun that. Trishatomy, incredible. I thought it was like a pun on like anatomy or something. I don't know if you were really into taking high school anatomy, but radical. We've got some goals. I love that. Set a goal for yourself. Try to beat your own personal record. You're only competing against yourself and everybody else. And yes, I think a great goal for everybody is to submit something by today. Oh, I think at the end we'll also talk about the Kaggle progression system, because it's kind of a fun little system that I like to share because I think it's neat. Okay, great. So our competition. Yeah, our competition is to take the data from this data set and try to predict the price of houses that have not sold yet, right? And if you come back over to, we should be able to. If you navigate back to this homepage here, you should be able to click on the data page, and you can see here's all the data that we have, right? So we can quickly just kind of run through. We have a list of all of our columns, and then you can see the actual spreadsheet down here if you click on train.csv. So we have ID, a random ID, totally meaningless. Stop asking about it. The zip code is obviously the zip code of the house that we're selling. The city is the city where the house is going to be sold. The state is the state where the house is sold. The date is the date where the house was sold. bathrooms, the number of bathrooms listed for the house, the number of bedrooms, the total amount of living area in square feet. So if you get on Zillow, these are kind of all things that you would see, right? You'd see how many bedrooms, how many bathrooms, how many square feet, the kind of home. So we have a single family. So that's like a normal house with like a yard and sometimes a driveway, but like a freestanding house. A condo is usually like kind of like in an apartment building, so like a giant building that has lots of units, but you own one of them. A townhouse that's actually what I live in. I live in a townhome. Is where you have sort of your own front and back, but you kind of share walls on the side. And then multifamily is when there's like a duplex or like maybe like a fourplex or eightplex, but you own the whole thing. So you own one building that has maybe 6 units in it or something like that. That's multifamily. And there are a couple others, but you can get a sense. But the most important one down here at the bottom is price, right? That is the thing that we are trying to predict. Because if we could predict how much a house is going to sell for, if we see a house selling for less than that, then we could buy it and we could make a great profit. Or alternatively, you could just check to see if you're getting ripped off if there's a house you want to buy. And if you come down and you click on train.csv right here, you kind of see a spreadsheet here where you get both a little summary, some histograms, and if you scroll over, you can see more of the columns. Some of them are hidden, so if you click right here, you can come down and you can click these to include them. You scroll all the way over, you can see we have price. And so this is train.csv, and train is basically our labeled examples, right? In machine learning, you always have to have generally speaking, you have some labeled examples that you learn from, and then you have some unlabeled test cases that you try to predict on. And so if you click on test.csv, this is actually where our challenge is. So if you scroll over, you will see, even if we click all of these, there's actually no price column. So this has all the same data, except we don't know how much it sold for, or if it's going to sell at all, or any of those things, right? And so that is kind of our task. And we touched on this a little bit at the very end, but if you click on sample submission, the thing that we will submit looks like this, where we just have an ID and a price. So these prices are how much the home sold for. And so we're just going to submit a file that looks like this. So you don't actually have to include all the rest of the data in the test set. So that's the data that we have for this competition. If you come and click back over on code, and then come and click on exploring our data, which is kind of where we already were, and you should be able to hit copy and edit. I just hit edit because it's mine. And we will see some code to do some analysis. So there is a thing called exploratory data analysis that if you see the acronym EDA, that will mean exploratory data analysis. And that means I don't have like a specific goal. I'm just kind of trying to figure out what's going on in this data set. And it's usually a pretty good place to start. If you don't know much about the data set, then just getting in and kind of taking a look at it is really important. All of these, actually, the first two here are libraries we covered yesterday. So Pandas kind of lets you import your data and kind of use it like a spreadsheet. Matplotlib lets you graph things. We use that a lot. NumPy has like a lot of different math functions in it for Python. A lot of numbers for Python, NumPy. And then Seaborn actually just makes our graphs look a little bit prettier. So then last time, we mostly created a data frame by saying pd.dataframe and then putting our data inside here. But a thing that you will actually do more often is importing a CSV. So the CSV file, that's what we were looking at earlier. It's kind of like, I mean, if you have a spreadsheet or like an Excel file, you can export it as a CSV. And our CSVs for this competition are right here. So the way that I got these little paths was just by hitting the copy file. And then, so I can hit copy file on train.csv, and I can paste it right there. And that's where that CSV is. So if I run this cell, and then I create a new cell and say train.head, I can see all of my data is here in my little Python script. And I think we should even be able to scroll over and see price right there. And then if we remove test, you can see we scroll over and there is no price. Any questions about the difference between the train set and the test set? This is something I think is pretty self-explanatory. I don't think it's very complex, but just getting that idea that we have one file that lets us learn and then another file that tests what we learned, basically. Or one file that has labels and one file that's unlabeled is another way that we'll put it. Cool. So as we saw in the last session, we have our data frame has a columns attribute that we can loop through to look at all of our columns. So if we just, before we even do this, if I just said train.columns, I get this list of index, zip code, city, all the things we talked through earlier. Let's see, dark rules. I'm getting an error by running first block. Okay, just a question. Are you doing this in the Kaggle environment? If you are, because if you're copying this and running it locally, that could be a cause of it. Because if you're following along in Kaggle, then that should make it easier, and all of the packages should be the same. I know sometimes some people do want to run it locally, and like totally understand that. But yeah, you can also do a pip install. Great suggestion, Asman Hadir. But yeah, mostly I would just recommend getting on Kaggle. If you're still having that issue on Kaggle, then we can dig a little deeper. Which I guess I think I mentioned this yesterday, but this is actually, I think, the main reason that I do like doing things on Kaggle. Obviously, you might have a more powerful computer at home, but just the simplicity of, oh yeah, all the things are taken care of, the versions are right and all that stuff. Because as we talked about yesterday, package managing in Python is not a fun time. Okay, so we can do train.columns, and we get all of our columns out, and we could loop through our columns. And for each column in our list of columns, remember, we can access an individual column just by using our square brackets around train. So for example, train, and then if I said zip code, we could get all of our zip codes. Oh, I am glad to hear that it is working for you now, Dark Rules. That's awesome. Hey, Crystal says, can we run only the current code block but not run all? If I click run beside the code block, it shows something is not defined, which is the code block above that. Yeah, so sometimes you can, like if you skip around, you'll get things undefined. I believe you can just click run, and you can click run all or run before. I like going through it sort of piece by piece just because I can then think about things individually. I think I mentioned this also. A nice trick is to do shift enter. So if I click just on this one and I do shift enter and then shift enter and then shift enter and then shift enter, it kind of like makes sure that I run all the things together. Yeah, great question. Okay, so we can grab a single column using our square brackets here. So we're getting just our zip codes in our data set. And so here we could put all this together in a loop where we loop through all of our columns and then grab each column individually, printing out the column. And then this is one I don't know if we touched on this yesterday, but dot value counts gives you the how many times each individual value shows up. So in our example, actually a better one for this is home type. So if we just grab a home type, and then we do dot value counts, then you can see how many times each type of home shows up. Also throughout, I think Kaggle is great, and the Kaggle environment is awesome. I love it. There are some times where there's just weirdness, and if you just run it again, like things just magically work the second time. There is actually a little bit of this weirdness from package managing, which is a conversation we don't have to get into today. Cool. So we see we have 19,000 single family homes, 2,000 condos, like about 2,000 townhomes, and then only 500 multifamilies. But for some of these, so this is fine. We could just see all of these. But for some of these, there will be, for example, for city, there will be like a gajillion of these, right? It gets really long. Yeah, so there are 4,300 different cities in our data set. So you can't actually see all of them. But if you want to get just the largest ones, then you can do dot n largest. So what if I just wanted the 5 largest cities? And you can just see, okay, here are just the 5 largest cities: Anchorage, Louisville, Cheyenne, Las Vegas, Indianapolis, which is interesting. These are not actually the largest cities, but they are the cities that we have the most data for, which is interesting to me. Cool. So we've constructed this little guy here, and so that's just what we're doing inside of our loop here. And if we run this, we can see, okay, IDs. Obviously, our IDs are random, and so they don't mean anything, and there's only one of each of them. That's what makes it an ID. Our zip codes, okay, we have some zip codes that are more common than others. Actually, this one zip code is like really common. I wonder what zip code that is. That is Cheyenne. Interesting. A lot of real estate data from Cheyenne in our data set. And then Anchorage is the most common city, which is interesting. States. This is super weird. I mean, this is kind of a first pass at looking at your data. It looks like we have more data from Connecticut than any other state, which is kind of interesting. Date sold. You can see they seem to cluster basically all around the same dates. All these dates are close, but we don't really get too deep into that. Number of bathrooms. So yeah, it's like really common for a home to have 2 bathrooms. After that, 3 bathrooms is pretty common. 1 bathroom is pretty common. 4 bathrooms is uncommon. 5 bathrooms is uncommon. I would guess it's pretty uncommon to have 0 bathrooms, but I don't know. I've seen some condos in New York City that are like, yeah, shared public bathroom that you can go to. Living area. This is kind of interesting. It's like, yeah, because these are just numbers, they're kind of all over the place, but there definitely are some that come up more often. Home type, we already saw this. Single family is the most common, then condo and townhomes are less common. Home status, recently sold and pending, kind of interesting. NYC real estate is insane. Yeah, my boyfriend Richard and I, we have talked about it at some point about like, oh, would we live in New York City? And on the one hand, it is an incredible place to be. Like, it's so much fun, and also it's like a nightmare, right? I enjoy visiting there, but yeah. Well, I don't know if I would live there. Yeah, this is, I definitely have run up against this in a Kaggle notebook where I just need to rerun it. There's also a weird thing where if you import something, but then you install a new version, this is not that weird, but you'll still have the old version because it was already cached. Sometimes you have to install first and then reload your notebook and then import it again. Lots of fun, weird things. Let's see, lot area. So this is kind of interesting. A lot of places say the lot is 0. So lot is just the amount of like ground that you are built on, right? And so kind of by definition, if you're in a condo, there's no like land that is just your land, right? In a townhome, you have some amount of land, right? I have, I don't know, like 500 square feet of land beneath me or something like that. But so you can see these are sort of the most common thing is to not have any land attached to your place, which kind of makes sense. But then this is interesting. We have lot unit. So the lot sometimes is measured in square feet, but sometimes the lot is measured in acres. And so this is something we'll have to deal with, because you just said, if I have 1 acre of land and you have 100 square feet, like your number is bigger, but like I have more land than you. So it would be silly if our model couldn't recognize that. That would be, an issue. Address. This is super interesting. I'm not sure I guess that either this is the address of some kind of like apartment building. Otherwise, it would be weird that this address shows up 4 times. Then price is what we're trying to predict. And I guess this is not crazy, right? Like a lot of, especially when you list something, a lot of people will just pick kind of a nice even number. A lot of people will say, yeah, this house is $250,000. Yeah, this house is $300,000. But I would imagine it has a pretty long tail of, just like, this house is $241,621. That would, not show up at the top of our list here. I have some notes here. Yeah, so zip code looks interesting, but we'll have to deal with that a little bit later. City and state these are categorical variables. Date sold probably isn't actually that helpful because we all know that these were supposed to have occurred around we know all of these occurred around the same time. I grabbed all this data from the internet at like the same day, basically. Bathrooms. This is kind of where we're starting getting into our bread and butter as machine learning scientists. This is sort of like a classic good integer variable that we can mess around with. Bedrooms, similar. Living areas, good. Home type is interesting, and it's good to know we only have 4 types of homes. Home status. This is actually one we didn't talk about, but this is important because some of the houses haven't actually sold. We actually just want to filter those ones out, right? We don't want to look at any homes that haven't actually sold because that's not actually reliable data. We talked about lot area and lot unit here, how the lot area could be square feet or acres. Address is probably too specific for us to be useful. And then price, which is what we're trying to predict. Cool. Weird selling quirk for NYC. 8 is a lucky number in China/Asia, so including 8s in your price is helpful. That is super interesting. Huh. If I ever sell my house, I will sell it for whatever the number is and $8. Right on. Okay, so we're going to filter out. The first thing we can do is we can filter out just the things that have sold, right? So remember, we can get a list of trues and falses just by checking, is this column equal to recently sold? And mostly it's true, right? Like most of these have actually sold. And so we can filter that out. And then we want to do this dot copy. If you remember from yesterday, if you don't copy it, that will continue to be a slice of our original data set. And that can lead to some weird behavior later on. Let's see. Oh, at first I was thinking I should push that out. Maybe actually no, we can get rid of it. Oh, also let me know. These are the ones, the housekeeping items I'll always say. If I'm talking too fast, let me know. And if my screen is too small for you, let me know. And maybe actually right now we'll just kick it up one size there. Okay, cool. So we can make a copy of it so we have like a whole new data set that we can mess with. So this is training, but only the stuff we sold. And then we can actually drop home status column because we don't need it anymore. So this is something we didn't cover, but you can do dot drop and then the name of the column you want to drop. And then axis equals 1 is a weird thing that you have to put in because otherwise it will think that you're trying to drop a row. And so axis 1 just means column. So axis 0 is rows and axis 1 is columns. And then we can print it out just to see what that looks like. Nanotubular asks, why do we need a dot copy if we're creating a new variable anyway? This is a great question. So this is, we touched on it yesterday, so in Python, when you have these sort of large objects that have lots of data in them, Python generally doesn't want to copy things by default because it takes a lot of extra space and time to make a copy. And so when you have a filter expression like this, the thing that gets spit out, even though you put it into a new variable, it will actually be a reference to your old data frame. And in a lot of cases, this is actually fine. In a lot of cases, you actually don't mind this at all, and it's actually useful because you don't want to use up extra memory. But it means that weird things can happen if you try to update or like change your data in your slice or your filtered version because it actually references the original one. So this is actually, I mean, I don't know. I would say the dot copy is kind of optional. Like there aren't any issues so big that you can't get around them. But it's just kind of nice and clean to say we're filtering it and it's just a whole new data set now. But good question. Cool. So now we have our data set and our home status is gone now. So this is we're now kind of shifting. We'll do some more data and proper analysis where we make some graphs and stuff. But we also are kind of going through this process of cleaning our data, right? We want to get just the data that's really going to help us. And so we're going to try to get rid of stuff that isn't helpful to us. Okay, so we said we probably don't care about date sold, but let's look at those values. This is sort of a classic thing we can use matplotlib for. So plt.hist gives us a histogram. And that is basically, it just shows you how often different values show up. So if we hit return, oh, wait, train only sold. Trying to run this again. Train only sold. Okay, that's weird. Okay, so I'll say we won't actually go, we won't go into detail on this, But these, so you could say, wait, how is that a date? That doesn't look like a date at all. And this is a sort of a Linux timestamp, which is technically a number of seconds after a particular date in the 70s. And it is what we use for dates often in computer science. But really, all you have to know is that, like, yeah, if these numbers are really far apart, then the dates are far apart. And if they're really close, the dates are close. And all of these actually really cluster together. And so, yeah, they basically were all sold around the same time. So we can safely drop that as well. So we can say train only sold, drop date sold. And again, we're passing access 1 because this is a column and not a row. So if I run this again, our data frame has gotten even a little bit smaller, even a little bit easier to deal with. We love this. Yes, I think we'll get to address in a second. But yeah, I think we'll just drop that as well. Address looks weird in the data. Interesting. Yeah, I mean, we could talk about address. I think the easiest thing to do is just get rid of it. I included it just because, like, oh yeah, these are real, these are real places that you can look at. And if you wanted to, you could, you could go and check to see. Yeah, that's real. And its estimate is 363,000. And it sold for 358,000. So it's gained a little value. There you go. Oh yeah, I actually mentioned this earlier. Yeah, so with the addresses, when we were looking at the frequencies up here, I called out oh yeah, like that's kind of weird. My guess would be that maybe this is an apartment building of some sort. But it's also possible that there's sort of an error in our data set, and this is something that you'd want to clean up. If there are repeats of the exact same thing, then you'd want to remove those. Oh, no worries. I don't know how to format Twitch chat either. So, and even if you did, I'm on StreamYard, so it might not look right to me. But yeah, I think everybody should support Markdown style backticks. But yeah, no, that's certainly like a question mark that we could dive into deeper if we wanted to. Okay, so we're getting rid of date sold. Our data frame is getting a little bit cleaner, a little bit smaller. Yeah, we could also just drop address as well. If we have time later, we could maybe dive a little bit deeper on those repeats and see what's going on there. But now it's real small, right? And you'll learn to, as you do more machine learning, which, I mean, some of y'all are pros. I don't want to lecture you, except that's literally what we're doing. I'm kind of doing a live stream. But you'll get this sense for just how a data frame looks. And like if you go back up to our original head, like this is just for how big it is and how much random text there is. Like this makes me feel kind of icky. And then by the time we get down here, like, oh, like it fits on one screen. All of the values look really sane. Like this is great. You start to just like a data frame that looks right. We can also drop the ID. That's not going to do anything for us right now. Just getting a little bit smaller. And then why don't we take a look at our numerical columns? So there are a couple. It's interesting. This is actually kind of what we talked about yesterday with different data types. But in data science, we talk about different kinds of variables, which are a little bit different than our Python data types. So we can think about numerical data. Technically, within numerical, you can have different kinds of numerical data. So for example, like you could have ordinal data, which is like were you first, second, or third in a race. You can also have integer data and float data, which that's pretty normal. You can also have sort of ratios, right? So if it's between 0 and 1, that's like that's a different kind of number, sort of. And then you can have categorical data, right? So technically, like even zip code. Zip code is not really a number, right? You can't add two numbers together and have that mean something. Zip code is really a category, right? You are either in that zip code or you're not. City and state are the same. Home type is the same as well. Lot unit is the same. But the rest of these are all numbers: bathrooms, bedrooms, living area, lot area, and price. And so we could even come up with a list of all of our numerical variables to just analyze those. So if we do a loop through our numerical variables, we can do figure with fig size just tells us exactly how big it will be. So you can see this is the width and then the height. And then plt.title with the variable in there is the actual column we want to see. So you can see bathrooms shows up when we pass bathrooms. And then we can also do a histogram just to see sort of the distribution of our data. So if we run this, You can see bathrooms. We talked about this. It's very common to have 1 or 2 bathrooms. It's less common to have 3 or 4 bathrooms. And then once you get to sort of 5 and above, it's really, really rare. But you can see the graph goes all the way up to 17. So like that implies that somebody out here has 17 bathrooms, right? Bedrooms. Okay, this is kind of bazonkers. So this is a case where maybe a histogram is not quite as helpful, at least not yet, because it says, yeah, a lot of people have less than 2,000 bedrooms, and like apparently somebody has 14,000 bedrooms. So this is like a very skewed variable. Living area. Okay, this one maybe makes a little more sense. Like you see a lot of houses are around maybe the 1,800 square feet, maybe 2,000, and then they become less common as they go up. It looks pretty uncommon to have a dwelling that's less than like 500 square feet. That becomes less common as well. Lot area. Now this, pop quiz. Take a second, look at this graph. I think this graph is kind of funny, and there's a reason that we talked about earlier why. Guess in the chat, why does this graph look this way? And there are kind of 2 answers. There are kind of 2 reasons this graph looks weird like this. And if you remember, the histogram just means that because this number is high, there are a lot of things that have, a lot area of like between 0 and 1,000. And then there are fewer lots that have lot area of like 10,000. Okay, yeah. So, okay, great. Some folks got some good answers. Lots without houses. Apartment owners don't have land. Yes. So these are like good answers. If you have an apartment, it's just going to be 0, which makes sense. And then yes, okay, yeah, y'all got the other one as well. The units. Remember, some of these are in acres and some of these are in square feet. I think acres is technically just not the metric system. I don't know if it's common to use like square meters or square kilometers in other places, but acres are just like a really large unit of land. So if you live on an acre, you have like a large yard, basically. Yeah, so this is like it's a different thing. We all got it as well. And so you could be a really, really large, you could have a really, really large yard and have like 2 acres, and that still has you like way down here. Or you might have half an acre, and that's still a decently sized yard, and you'll be way down here. But if for whatever reason you entered it in the data set as, oh, I don't have an acre, I have 10,000 square feet of land, it would show up as 10,000, right? So that's just sort of a weird detail that we'll have to deal with for sure. And then price. Okay, price actually, of all of these, price kind of looks the most normal, right? You have, I guess it was living area also looks kind of normal. With price, you have this kind of nice slope where you can see it's weird. It's in scientific notation. So 0.25 actually means 250,000. So you got a lot of homes for around 250,000. You got, fewer for 500,000. You got a couple for 750,000. And that is the little curve there. So yeah, all of these are pretty skewed. In data science, skew just means it kind of slopes to one side, right? If you had a normal curve, it would be basically symmetrical. But if you have one side that sticks way out, or if you have people talk about having a long tail, then that is what being skewed means. And this is usually an indicator that there's some outliers. And outliers can make our analysis tricky. There are a lot of ways to deal with outliers, but if you don't have too many of them, a really easy way to get rid of outliers is just to literally get rid of them, right? And so if we come back up here, like bedrooms. Okay, yeah, so we have a lot of things, like almost everybody has a relatively small number of bedrooms. And then apparently there's a data point out here that has like 14,000 bedrooms. Probably including that data point in our analysis and our model is not actually going to help us that much, right? And if you come across a home that has 14,000 bedrooms, like maybe that's just bizarre and it's not going to be easy to predict on anyway. And we don't want to mess up sort of the rest of our, because like, oh yeah, if you looked at this and I asked you, well, how many rooms does the average home have? You would guess like 4,000 rooms, which is obviously wrong, right? So we can just get rid of our outliers. Now, That's before we get rid of our outliers. There's actually another thing we should do, which is this thing we talked about, which is reconciling our lot area. Sometimes is in square feet and sometimes is in acres. And so we should just convert everything into square feet. That'll just be easier to work with. And every acre is 43,000 square feet. So that makes it easy to just multiply by that number, and you can go from lot area acres to lot area square feet. So we touched on how to make functions yesterday. And so this is a really easy way to change a value in your data set is to just make a function that accepts a row. So it'll accept one row of data and it will spit out our new updated value. And so a row is kind of like a dictionary where we can look at each column in the row just with our brackets, just like we do for a data frame. So we can say if our lot unit is equal to acres, then the thing we should return is the number of acres multiplied by 43,560. Otherwise, that means the square feet, and we can just return that number. If you have any questions about just this function, all it does is it accepts one row from our data frame and then spits out a new value of our lot area. Yeah, okay. Ratcat fully throwing off all of our data analysis with your very large castle. So we can define this function, and then in order to run that function on all of our data, you can use the data frame and then use dot apply, and then you can pass the function you want it to apply. So this is a little bit of a different way of thinking about things. Normally we define a function and we just call it by saying like function, and then here's my stuff in the function, right? But when we're using a data frame, it's called sort of being more functional, where you define a function and then you just say, hey, this is the function that I want you to do to all of my data. So when we say apply, we're asking it to apply this function to all of our data and then give us the result. And so that result is going to be an updated value for lot area. And so we can just assign it back to our lot area column. So if we run this, if we compare to up above, well, we have to compare it quite a bit up above. I guess we could actually just come down and look at what it looks like. So we have a lot more high numbers. And so like where it used to be acres, now this number is really high because it's actually in square feet. So now let's plot that. And okay, cool. Now this suddenly looks a lot more appropriate, right? So we have lots of things that have, not that large of a yard. And then we have some things that have larger yards, right? But it doesn't do that weird sort of like hump thing that looked kind of strange. Great. But this still has a lot of outliers, so we might want to deal with that. Why does the fourth index row still showing acres? Yeah, so that's a great question. So what we're doing here is we're only overriding lot area. So we're using the lot unit column and lot area to come up with this new number. But the only thing we're actually changing is lot area. And so I think I do this later. But yeah, after we've done this conversion, lot unit doesn't actually mean anything because we've already changed it around. And so we could, I think I drop it later anyway, but we could just say drop lot unit axis equals 1. And that probably is it's probably a good thing to do just to keep it less confusing. Yeah, exactly. Good question. Good catch. So this looks good. Okay, so let's deal with outliers. And this is actually going to get a little bit statistical. So I don't know if you actually here's a good question. Statistics. I would love on a scale of 1 to let's do 0 to 4, where 0 is like I've never heard the word statistics before, and 5 is I have a degree in statistics. And maybe 4 is I have a degree in statistics, and maybe a 2 or a 3 is I'm pretty comfortable with with taking the variance of something or the standard deviation or stuff like that. And then a 1 is I know what an average is. In the chat, drop your comfort with statistics. So 0 is I don't know any statistics, and then 4 is I am a stats pro. Okay, cool. We don't have anyone at the super high end. Oh, okay, someone studies math. So Afrozeus is probably saying statistics is not real math, which I agree. I think statistics is a sham. Okay, so lots of folks didn't know, which this is great. So let's talk about here's what we'll do. Let me see if I can find a good graph of. Okay, sure. I'll look at this one. This is from. Oh wait, open image, new tab. Don't worry, I will show you this in a second. I just got to make my screen look pretty for y'all. You know, I have high standards. Okay, cool. So this is what we call a normal distribution. And an easy way that you can think about this is it's kind of just a histogram. It shows you in the middle where most things fall, and then as you move further out to things that are super high, numbers that are high or low, they become less common. And these numbers here are for a classical normal distribution. What percentage of things will fall in this section? So right in this section, 34.1% of all of the stuff happens in that little section. And as you go further out, 13.6% of the stuff happens in this little section of our graph, right? And the way we're chopping this up is by standard deviations. So the math around a standard deviation is, honestly, I won't go too deep on it, but it sort of involves this relationship between sort of the mean and the average distance from the mean. But it is a nice way to chunk up. If I say that you are one standard deviation above the mean, then that means that you're not crazy high, but you're definitely higher than average, right? And if I say that you're 2 standard deviations below the mean, that means you'd be 1, 2 standard deviations below the mean. Like suddenly, like you are like anomalously low in whatever number we're looking at, right? Like say this was price. And if I said, oh yeah, this house is priced at 2 standard deviations below the mean, that would mean like, okay, that's definitely on the lower side. And then if we go all the way down, 3 standard deviations below the mean, that's like this is crazy, right? Like only 0.1% of things are that low, right? So that is a standard deviation. We also have actually, I really shouldn't have talked about standard deviations because we also want to talk about interquartile range. Let's see. Let's see if I can find a good graph for this. Yeah, this one's fine. I won't pull it up as good. But so you can imagine another version of this where we just chop our data into 4 groups called quartiles, right? So the bottom 25% of your data is here, and the sort of the second 25% of your data is here, and so on and so forth. And the interquartile range is just how different is your 25th percentile and your 75th percentile. So like that cluster of stuff that falls in the middle, how spread out is that? And that is interquartile range. And so I don't actually know if that's true. Stats people will have to check me on this, but interquartile range and standard deviation are 2 different sort of measures of spread that we can use to see how spread out is our data. And so the idea of finding an outlier is anything that is really, really spread out there, right? Okay, yeah, Samaha forgot all of their stats. There are a lot of stats things that's like, oh yeah, I just told you about standard deviation and interquartile range because I didn't remember which one that you use for outliers. Okay, actually, we'll take a brief intermission from stats because School Crusher for Life asks, what's axis equal 1? Yeah, so this is a great question. And honestly, if I was rewriting this library, I might say just have the default axis be 1 because people use that a lot. The simple answer is that axis equals 0 means rows, and axis equals 1 is columns. So if you have, a spreadsheet, you have rows and columns. Your 0th axis is the rows, and then your first axis is the columns. And so because we're dropping a column and not a row, we just say axis equals 1. But honestly, if I could, I would just say make the default 1 because that's usually what people do. But good question. Yeah, Dark Rules got it right. Well done. Okay, cool. So remember, we can do just arbitrary arithmetic with our columns. So if we wanted to say number of bedrooms times 2, this now gives us, see, all of these are the number of bedrooms it has multiplied by 2, right? We could do number of bedrooms minus 2. And so now we have, a lot of low numbers, right? But you can also do functions on it, like, for example, getting the mean. So what is the average number of bedrooms? Cool. So the average number of bedrooms is 3.8. Honestly, that's kind of big, which I guess that's down to the mean gets overly influenced by outliers, which is what we're here to deal with. But so the mean is 3.83. On average, people have, about 4 bedrooms. So what we can do is we can actually take the number of bedrooms that you have and subtract the mean out. And this is, we're getting a little bit mathy. Yeah, no, I think Afrozeus, I think that you are correct here, and I use standard deviations instead of this, but sort of the same concept applies. I'm going to continue with standard deviations, but know that this is not like technically the right definition of an outlier for sure. Okay, cool. So the number that we get here is basically, do you have more than the average number of bedrooms or less than the average number of bedrooms, right? So if you have 0.16, that means you have just a little bit more bedroom than average. Or if you have 1.6, oh, you have like, almost one whole more bedroom than the average house. But if you have negative 1.8, that means, oh, you have like, not quite as many bedrooms as the average person. So yeah, I like this comment. It says, if you remember from stats class, an outlier is this thing, but that's not actually what an outlier is. So that's great. I did not remember from stats class. But there are lots of different ways that you can just try to find things that are, that are out of the ordinary. And this is one of them. So we're now creating basically a new column called distance from mean. And this is just this number, but we do the absolute value of it. And so all of these numbers, but just positive. So you can see all the positive numbers stay the same. So 0.16 stays 0.16. But then if you come down here, negative 1.8 just turns back into 1.8. So now you can easily grab the standard deviation as well, and you can multiply by 3. So our standard deviation times 3 is 298. Of course, there are different ways that you could measure this, but this is one. So now if we actually want to get things that are relatively close to normal and get rid of things that should be outliers, then we can just do a filter expression where we say, if your distance from the mean is less than 3 standard deviations, then I want to keep you. Otherwise, I want to filter you out. And then we can just grab bedrooms. So this is just bedrooms without outliers. And we can graph this to see what this looks like. Oh, did I not run distance from mean? Distance from mean. Cool. Okay, so we have both bedrooms with outliers and then bedrooms without outliers. So this is our original graph, right? Because we have, oh yeah, somebody has 14,000 bedrooms or whatever. But if we then look at bedrooms without outliers, okay, suddenly this graph, I mean, it still is kind of lopsided, but it looks a lot more sane. Now it looks like the person with the highest number of bedrooms has like 30 bedrooms and not 14,000. And you can see we get a little bit more sort of granularity. Another thing that you can do just to be a little bit more precise is into the histogram, you can pass a bins parameter. So you could say bins is equal to 100. And so that just means it'll chunk it up into 100 little sections. And sometimes that gives you sort of a better sense. So you can see here it's still just, so lopsided. And then down here, you can see, okay, yeah, we get a little bit, a little bit more information that, you have lots of places with 1 bedroom or 2 bedrooms or 3 bedrooms. And then once you get to 5 or 6 bedrooms, that becomes less common. Which plot would be the best for data with outliers? Yeah, that's a good question. I mean, usually if you have outliers, the problem it'll just mess with how you zoom, right? It'll just squish everything together. I mean, for discovering if you have outliers, one actually that I like, I don't know if we use this later, is a violin plot. It's basically a box plot with a little density diagram on top of it. Yeah, a box plot is also good. But I think a violin plot is more fun. And so I'm going to, let's see, I think it is sns.violin plot. And we should be able to just pass bedrooms. Let's see. Okay, yeah. So this violin plot obviously like just doesn't look very good because it is so lopsided. So this just like makes it very clear there's this one outlier out here or a few outliers. But then if we come and we grab bedrooms without outliers as the data that we put in our violin plot, it looks a lot nicer. Okay, a lot nicer might be a bit of a stretch, but it looks nicer, right? Looks a bit nicer. Let's see. If we're moving, yeah, box plot also is good. So there you can see even after we remove outliers, because once you remove outliers, your data set gets smaller. You technically could create more outliers, right? And so here you can see there are still these, the places that have 30 bedrooms are still outliers, right? And so you could do this. You could be even more aggressive, right? You could, as we're doing a calculation, you could just say, actually, I'm removing anything that's 2 standard deviations away from it. And so that'll be, a little bit more aggressive. That actually didn't do much. You could also just literally cap it, right? You could say, I'm going to get rid of anything that has more than 10 bedrooms. But let's see, School for Question for Life. If you're removing outliers from the training set, do you check the test set to see how many outliers are in that set because they're probably going to be pretty off? Yeah, I think this is generally speaking a good idea. This is maybe something that I'll leave for if folks want to do this. This is maybe an edge that you could get for yourselves. I think usually the way that that many people think about this in modeling is if you have something that is truly an outlier, that is really outside the realm of where regular data shows up, then you almost are kind of saying, if it's that crazy, then I don't think I have a great chance of dealing with it anyway. I think it's a good idea to check to see, how many outliers are there. But generally speaking, there are not that many. Or I guess the other way of putting it is there should be roughly the same amount of outliers in your test set as there are in your training set, right? We could actually do this relatively easy if we wanted to just check how many outliers are in the data set or in the test set. So we could do test bedrooms minus our mean, and you actually technically want to use the same mean from your training data set because that's how you're scaling it. Yeah, Darkles, this is a good point, and it's maybe something that we mess with a little bit here. I think it's a little bit weird because it's an integer that we think of it as an integer, and there might be some data in there that's actually a non-integer value, which is maybe something we could look at and try to fix. So if we do test distance from mean, and then we could just check how many or we could even just we could find how many cases is test distance from mean. I actually need to do the absolute value. In how many cases, not is it less than, but how many cases is it actually greater than? That's interesting. We think that's right. I guess it's all of them or less. We could even just look at this visually. And it's actually, so our test set is actually much more sort of centrally located. It doesn't have as many things that are way out there. So this is actually even more of a testament to the idea that maybe maybe including those outliers in there is not going to be helpful for us because our, we could even just do a histogram of bedrooms. So yeah, our test set actually is a lot cleaner in this sense that we don't have crazy numbers, which just because our test set is smaller, it does make it less likely that we would have those crazy outliers. So that kind of makes sense. Okay, Dirk Rule says, I'm confused, is number of bedroom variable acting as categorical variable here? Yeah. So this is a great question. This is something I don't actually think we touched on. When you have a data frame, you can, there are a number of things you could do, but you can look at the data type. So the data type here is technically a float. Most of our numbers are integers. So if we come here and do value counts, so you see pretty much everybody is an integer. And then we have these rare cases, like for whatever reason, lots of things have 3.7 bedrooms. And I think this actually is probably a number that is, when this data set was created, I think this is actually the average, and that there was some, for whatever reason, not a number there. And so they put the average in the place instead. And that's how you get a non-integer number. And you could imagine saying, no, that seems like garbage. Either throw out those rows or say, I'm just going to turn that into a 3. But because it is, in fact, like a thing we expect to be an integer, it does almost kind of act like a categorical variable, but it is a number, right? But yeah, so if you saw sort of the weirdness here, that is because of that. Let's see. Yeah, bathrooms are weird. Yeah, because people will talk about something being a half bath, right? If you have just a sink, that's maybe a quarter bath. And if you have just a sink and a toilet, maybe that's a half bath. And if you have a sink and a toilet and a standing shower, maybe that's 3/4 bath. And if you have a sink, bath or a bathtub, a shower, and a toilet, maybe that's a whole bath. But these things are not, I don't think they're super standardized, which that'll be interesting actually to look at in a second. Cool. So we did some math on outliers, and yeah, I don't know why I said multiply by 5 here. We can say multiply by 3, which I'll do my disclaimer again. This is not technically an outlier, but it's an idea that gets kind of close to the idea of what an outlier is. In fact, probably even 2 standard deviations. So this is us just doing that same thing for all of our numerical columns. So we're just replacing our numerical column with our numerical column with no outliers. And now we should actually check how many outliers did we remove. So before we removed outliers, we had 23,000, and then after we removed outliers, we have 19,000. So maybe 2 standard deviations is a little aggressive. Maybe we could change it back to 3, because at that point we're dropping like 4,000, or almost, we're dropping like 3,000 rows. So maybe if we run this again, okay, yeah. So here we're dropping like just a little over 1,000 rows, and that maybe seems a little more reasonable. So now we're just going to rerun all of our graphs, and I picked bin 7, which I guess we'll just see what that does. And cool, bathrooms now makes a little bit more sense. That looks, well, kind of. The numbers are a little bit weird because it doesn't bin directly on the integer. Bedrooms, okay, yeah, we know we still have a house that has 30 bedrooms, but like, a house with 30 bedrooms, sure, that exists. Like that's not like a fluke or anything. Living area, this curve now looks super nice. It kind of tops off at around 4,000 square feet, which like 4,000 square feet, like that's a large house, but that's, you don't see too many houses that are like 10,000 square feet. Lot area, this also now looks a little bit nicer. Yeah, most places are relatively small. But then, you certainly have this sort of gentle slope to things that go higher. And then price also looks nice. And it looks like our most expensive houses are around $800,000. Cool. So now that we've done a little bit of cleaning and removing of outliers, we can do something called, actually, so far, really what we've done has been called univariate analysis. These are our little vocab words. Like in Intro to Python, we talked about concatenation, univariate analysis. If we break it down, unit just means one, and variate is like variable. So univariate analysis is just looking at one variable at a time, right? So here we're just looking at price, right? And here we're just looking at lot area. But there are lots of different ways that you can look at multiple variables sort of together, right? You can look at how two variables interact. So like, I mean, like one very simple thing that you could do is you could just do a scatter plot of maybe bedrooms and let's do a scatter plot of bedrooms and price. So there you go. You have, that. I mean, that doesn't look super. Okay, let's look at bedrooms and bathrooms. Maybe that'll be a more fun thing to look at. Okay, cool. So we have bedrooms on the x-axis and bathrooms on the y-axis. And this is interesting. It's like even as you start adding, which actually now we're looking at this, there's really just this one outlier here, which I kind of wish we could get rid of. But actually, because we have that one outlier there, I actually do kind of want to get rid of it. Let's just get rid of anything that has more than 10 bedrooms. That would just be easy, right? What if right after we do outlier removal? Sorry, I'm sure I'm giving you vertigo just by scrolling up and down again and again. So let's also say we can do kind of like this. Bedrooms. We'll just filter it out based on bedrooms. We're just saying if you have more than 10 bedrooms, we're just going to throw you out. This is not super elegant, but it gets the job done. And yeah, we only lost one additional record. So now when we graph this, okay, our bedrooms graph also looks much nicer now. So bivariate analysis. Okay, cool. A little bit funky, but you can kind of see, okay, things generally kind of go up and to the right. You don't have any places that have 9 bedrooms, but only 1 bathroom. You also don't have any places that only have 1 bedroom and 5 bathrooms. Interestingly, there is a place that has only 1 bedroom and 3 bathrooms, and that's kind of funny, right? But so a scatter plot is one sort of easy way to do bivariate analysis. But maybe something that are both floats. You could do living area and price. And, okay, cool. This is like a little bit more like kind of what you'd expect to see. You can also actually make the color slightly transparent, which is sometimes kind of nice. So let's say we can do, it's RGB. So let's make these red. So we can do 1, 0, 0. But then you can do like 0.5. And so that'll make it a little bit transparent. In fact, okay, so you can see a little bit of the overlap there. But let's actually make it even more transparent so that when things are denser, you kind of see them. Okay, cool. This is a fun graph. It almost turns into a heat map here. But so you have on the x-axis, you have the living area. PLT title. PLT x label. Square feet. And then our y label is price USD. So you can see most of the houses, there are these things that are kind of up here, but most of these houses sort of follow this general trend of, yeah, as you get bigger, you get more expensive, right? And it's not exactly this straight line. It kind of, you kind of see like sure, there are some small places that are really expensive, but for the most part, you kind of angle up and to the right here. So that's an example of bivariate analysis. And it's kind of a good just intuition check. Like, yes, the more square feet there are, the more expensive it is, right? Another sort of classic thing you can do when you're investigating your data is a correlation heat map. So if you just do our basic data set and then do .core on it, and then pass that to SNS heat map, we get this cute graph where the more two things correlate, the sort of warmer it is, and the less two things correlate, the darker it is. So you can see on our diagonal here, so zip code and zip code, like, yeah, they're literally always the same, right? And bathrooms, they're literally always the same. So this is sort of the highest number. But then there are some things that that correlate more than others, right? So this is a relatively light thing, and living area and number of bathrooms and living area and number of bedrooms, like those seem to be pretty correlated, right? As you add more rooms, you kind of have to add more square feet. So that kind of makes sense. There's generally, you're not going to add a room that only has 2 square feet. So those things end up being kind of connected. But ultimately, we kind of want to look at price, right? Because price is what we're trying to predict. And you can see, okay, zip code kind of doesn't count, even though it's technically a number. It's, we really should think of it like a category. But bathrooms, the more bathrooms you got, the more expensive you are. Interestingly, bedrooms does not correlate as much with price because it's this, this darker color. Living area, that makes sense. And then really surprising to me, lot area doesn't correlate that much. Maybe one way. Actually, here's a question I'll put to y'all. Why might lot area not correlate with price as much as, say, living area? Answer in the chat if you have a guess, because I have a guess. I don't know for certain, but I have sort of an intuition about it. Any guesses? Let's see. Kaggle doesn't work like Git, so as you edit your code base during this talk, we won't see the older versions, right? Yes, that is. So there are versions. I don't know if you can see them publicly. So when I save a new version, I'll be able to go and see back in time. I don't actually know if you'll be able to see back in time. But that is a good question. But I'm mostly just adding stuff, so hopefully, hopefully it is useful. Cool. No guesses. Okay, so my guess, let me scroll back down to see if I can find where we were. So my guess is that generally speaking, things in cities, so like a house or an apartment or a townhome in a city is generally going to be more expensive than some place that is really in a really rural area. And the further into a more rural area you go, the more likely it is to have a bunch of land, right? And so you probably have examples of a place that has tons of land that is in the middle of nowhere and is therefore pretty cheap. This would kind of be my guess. And it's not like they're not correlated at all. They're just not that correlated, right? And in a sense, that makes sense because the more land you have, the more likely it is you're in kind of a cheap place. Yeah, I think this is also fair. I mean, like, just generally speaking, living area is more, like if I asked you, would you like a house that's twice as big or a yard that's twice as big? I mean, you might have different opinions, but like a lot of people probably value the living space more for sure. Good deal. Okay, so we've done a lot with our numerical data, but we have left our categorical data kind of without any love, right? So I think I definitely today want to talk about how to handle our categorical data. And the thing to sort of gesture to the future is when you feed data to a machine learning model, basically always it has to be a number, right? Even when you are talking to a chatbot, when you're typing into ChatGPT, the first step when your words go in there is they all get broken down into pieces and turned into numbers, right? And so ultimately, we need a way to turn all the data that we want to actually use into numbers. And right now, we could build a model just off of the stuff we have here, right? I think yesterday we built a model just off of taking the average price, and like that's a model. But there's probably a lot of sort of useful information in state, city, home, the state, city, zip code, and home type. So one strategy that we use a lot in machine learning and in data science is called one-hot encoding. And this is a really classic way of turning a categorical variable into a number. And so to explain one-hot encoding, I'm going to run through this example just with a very simple data frame. So what if we had a data frame full of, it's a single column and it's just a list of colors. Okay, so we have one column with 3 different categories. And what one-hot encoding does is for each of your categories, it gives you an additional column, and the values of that column are just, am I this thing or am I not? So instead of red, blue, red, green, it would be one column that says, are you red? One column that says, are you blue? And one column that says, are you green? And only one of those would be 1. So only one of them would be hot. And that is the category that you belong to. So if we, this is what we actually want to end up with, is a table that basically says, are you red? Are you blue? Are you green? Oh, I misspelled green. That's funny. Is green. Hee hee. And so you can see, okay, our first row that's red is true, and then is blue and is green is false. There you go. Pandas gives us a really easy way to do this transformation, and it's called get dummies. So dummy is just a word for the column that is the one-hot encoding. And so if we run this on our original colors dictionary or colors data frame, then we get this basically for free. Instead of true and false, it's 1s and 0s. But you can see we have color red is the same as is red, and it's 1 whenever it's true, and it's 0 whenever it's false. And so this is just a simple way of turning our categorical data into numerical data. Does that make sense? This is sort of the first, more out there machine learning concept we've thrown out. And if anybody has questions about one-hot encoding, definitely want to take a second to unpack. I'm sensing there are no questions. Cool. So one-hot encoding is a simple method that we could use, especially when we don't have that many categories, right? Because you're making a column for every category. If you have, a gajillion categories, then doing one-hot encoding is probably not your best bet. Yes, exactly. Yeah, the model is not going to turn a string into a column into a number for us, sort of for free. We have to do it kind of before we feed that data to our model. Yeah, so this is actually an example of feature engineering, right? We have one kind of input data, and we want to sort of craft it into a format where our model can slurp it up easily. And one thing I'll say is there are certainly ways that you could try to just give it text, right? So like one simple way that you could do this is you could say, well, hey, like underlying text is just numbers, right? You have, ASCII numbers. You could say, well, hey, just turn the text into an ASCII code, right? And you could use some padding, so you have like one giant number. But that just would not actually be as useful to your model, right? It's like if there's ever any work that we can do sort of before the fact for a model, we want to make it as easy on our model so we could just focus on learning the thing we want it to learn. Cool. So we can look at our training data set with train no outliers, and we can run get dummies on home type, because home type only has like 4 categories to it, right? And so here you can see it sort of expands out to home type condo, home type multifamily, home type single family, home type townhouse, right? And that has sort of gotten rid of our home type column and given us a new set of columns that will be more useful to our model. Let's see. Will the model warn you if columns haven't been converted into numbers? Yeah, this is a great question. Depending on the model, you will sort of get different behavior. Also, actually, there are some models that are happy to deal with strings. So like a decision tree is a classic one that like is fine with categorical data. And if you have a string, it'll just treat it like a category and it won't ask questions, right? So I don't want to overgeneralize, but most of the models that we think about sort of need it to be a number. And I think under the hood, basically, your decision tree is turning into a number. But this is something when we get into linear regression, which I think at this rate will probably be tomorrow. That is something that we can try out. But yeah, you will get the error might not be the most informative, but you will get an error. Cool. So we have, instead of one column, we have 4, but instead of a categorical column, we have 4. I mean, they're kind of Boolean columns, but we'll call them numbers. Cool. So what about states? So states, there are 50 of them. Technically in our data set, there are 51, right? Which I think actually, yeah, we do. If we just grab the length of the number of unique states, 51 because we have BC in there. And that would be a lot of columns, right? There is a rule of thumb in machine learning, and this, I don't know, this is not gospel, but one rule of thumb that people throw out is you always want to have more rows than you have columns, right? So if you have a data set of 100 examples and you have 1,000 columns, probably your model is not going to perform very well unless you rule out some of the columns. And there are a number of reasons for this. Generally speaking, it's just very hard to generalize when you have lots of information about each row, but you don't have that many rows, right? So 51 columns, that's right around the edge. Generally, I would say if you have a categorical variable that has like fewer than 10 categories, then one-to-hot encoding is a pretty decent option for you. If you're getting up to like 50 different categories, one-to-hot encoding in many cases might not be as good of an idea. So one thing that we could think about is, well, what useful information is in the state? And you could say, well, hey, there are expensive states to live in and there are cheaper states to live in. And if you are buying a home in a more expensive state, then maybe our model would want to know that's a more expensive state, right? So maybe we actually just want to get a sense of how expensive is the state. And then that's a number, right? You could say, on average, you're this expensive. And one simple way to do that is just say, well, what's the average price of a house there, right? From our training data, we can say, well, the average price of a house in DC is 500 grand, and the average price of a house in Texas is 200 grand. These are fake numbers. So one way we can do this is by doing train.groupby and then passing the state. And then this gives us when you do a group by, it lets you group by a certain variable, but the thing it returns is a little bit confusing. It is technically a group by object, but the thing that you can do that is nice is you can pull out a column, so say price, and then you can aggregate. We're getting a little bit into like some more complex aggregation territory, but one simple thing you can do is you can just say mean. So this is now for every state gets you the average home price. So we can grab that and say average home prices by state down here, and cool. So you can see Arkansas, the average home price is 350. But if we found a state that's maybe more expensive, like California, in California, the average home price is $731,000, right? So this captures some intuition that California is a more expensive state. If anybody has any questions about that concept, happy to field it. But so now if we come back to our training data set, okay, we still have our state here, but we can do a merge. And in Pandas, a merge is just a way of taking data from two different data frames and stitching it together, or merging it together. So we can say train.merge average home prices by state. And this is a little bit more of a sort of advanced Pandas topic. But the how parameter tells you basically what thing do you want to use as your base. And I'm using the left as my base because the training data set is what's important. And I just want to add the average home prices, which is on the right, to my training data set. So I'll say how equals left, and then I can say on. This is basically saying, well, what do you want to use as a connector between these two data frames? And both of them have a state. And so we're basically saying, well, find the state from the other data set and take the data for that state. And there's a lot of words. But if we run this, we can see, okay, we still have our state column. But if we scroll over, we have both. So here it's saying price X and price Y because both of them were called price. But price X is the actual price of the property. And then price Y is the average price for a house in that state. Now, the columns here are a little bit weird, so we're going to want to fix that. And one way, I don't know why I typed train again. One way we can fix that is just by reassigning the columns. So we can say, okay, create a column just called price and replace it with price X, and then create another column just called average state price and just replace it with Y. And then train.drop will just get rid of those original columns now that we've renamed them. There are more elegant ways to rename columns, but I want to limit the number of new things we introduce, and just passing around the columns is fine for our purposes. So now we've gotten rid of, or we haven't gotten rid of state yet, but we do have price and average price per state, or average state price. Any questions about why we're turning the state category into this average state price number, or how we did that? So we're really in the thick of sort of cleaning our data and doing feature engineering. And this is definitely like, there's a certain amount of where the rubber meets the road on machine learning is, people say it is both a science and an art. And there's, the science part of sort of knowing your statistics. And there's also the art part of sort of understanding, like, well, what's useful about this data, right? And you can, of course, iterate and try lots of different things, but it requires some creativity. It requires some problem solving and thinking about, well, what useful information does state hold? And the underlying intuition that, well, some states are expensive and some states are cheap is sort of a useful thing to come up with here. So that's why we're turning it into an average state price. Cool. So now we've done some more cleaning and pre-processing. What I want to do is to stitch all of what we just did together into a single cell so that we can use it later on. And this is for actually multiple reasons. One of the reasons is because we can copy and paste it. The other one is because whatever we do to our training set, we also want to be able to do to our test set, right? Like if we, and we talked about this, like, well, yeah, if we are like converting square feet to acres or acres to square feet in our test set, you also need to convert acres to square feet in our train set. Interestingly, I decided to leave removal of outliers out from this just because it gets a little bit tricky, as we were talking about earlier. But this one cell now has everything that we did, which we can do a little review. So we import our train and test sets. We get our average home prices by state from our training set, which is useful because this is not going to show up in our test set. We have our function for converting lot area. We just multiply by the number of square feet in a lot or in an acre. We drop all those columns we don't care about. Then we can convert our lot area from acres to square feet. Then we can drop lot unit. We can also one-hot encode home type to get a new data frame with more columns. Then we can merge in our information about our state prices, which is useful. And then this is if price is in our list of columns. This basically means if we're looking at our training set, then we actually want to shift things around because we have two prices in there. But if price is not in our data set, then that means that we're in our test set, and that means we don't actually care about, or we can just directly assign price to our average state price. Wait, is that right? If price is in columns, this should be what we do for training. Does that work? So now we're cleaning our preprocess, and we're pre-processing our train, and we're pre-processing our test. And if we look at this, we get spat out just beautiful numbers. And then if we run this one as well, we get just beautiful numbers, but without price. Let's see. The Grinch Watches says, how does .group by work? Great question. So honestly, the way that I think about how Pandas works for aggregation, it actually I think about SQL. So if you ever have used SQL, it is a language. It's SQL, stands for Structured Query Language, but it is a language for getting data out of databases. And in SQL, there is an idea of a group by statement, and Pandas basically just borrows from SQL this idea of a group by. And so what group by does is it says, hey, you have some value that's like a category, and I'm going to go and grab for each category, I'm going to go and group all the data for that category into one little group, right? The next step, a group by itself doesn't really make any sense because it's like, yeah, the data is still all here. Like, what do you want me to do with it? And so usually the next step when you have done a group by is to aggregate it somehow, right? So you could say, hey, I want you to aggregate by state, or I want you to group by state, and then I want the highest number in each state, right? So that would be a max function, and a max is a way of aggregating. You could also say, I want the minimum number, and that would say, okay, for every state, give me the smallest number. You could also say group by state, and then give me the variance, right? So variance is another way of aggregating. You could also say, give me the average, right? So that's what we're doing is we're saying group by every state, and then once you have those groups, just do the average around the, just do the average inside the group. So you're getting just the average for things in Texas, and just the average for things in Illinois, and so on and so forth. Yeah, this is also a great point. Bug Breaker makes a good point, is that if you want to, you can get more. So a common thing you'll do when you're missing data is just grab the average. So like we saw, the number 3.7 bedrooms shows up. And that's probably because that's the average number of bedrooms, and people just filled in the blank with an empty number. But something that might be more powerful is to say, well, actually, tell me how many bedrooms on average houses have in Illinois, or how many bedrooms on average houses have in this zip code. And if you aggregate and then get your average to impute, that can make the thing you fill in the blank with, it can make it more accurate. That's a great point. What is the difference between concat and merge? Oh, this is a great question. So really the simplest way that I can put this is a concat is you're just sticking the spreadsheet, you're just kind of pasting it into the end, right? You're just making your spreadsheet longer. Whereas for merge, you are adding rows to your spreadsheet. Sorry, you're adding columns to your spreadsheet. So concat, if you have two spreadsheets that look exactly the same, but they're just different data, you can just add them together to make one long spreadsheet. Whereas if you have two different spreadsheets that they're about the same rows, but they have different columns, then you can merge them. So concat joins rows and merge joins columns. Hopefully that makes sense. The Grinch watches. I'm so glad that makes sense, because like it is, I don't know, group by, it can get very abstract and heady very easily, but y'all are brilliant, and so it makes sense. Ruthie, I'm so glad that makes sense as well. Incredible. Okay, so now we have done our cleaning, and I think that's where we're going to leave it for today. We can come back raring to really dig into, we'll do sort of a simple model building, we'll do linear regression, and we might even get into neural networks if we have time. But before we do that, I'm just going to revisit, or before we leave, I'm going to revisit, here, I'll save a version so you can see everything we updated today. If we go back here, cool. So I want to come back to submitting. So this is what we're going to look at tomorrow, is we are going to actually build more intelligent models and submit. But this is your basic template of how to submit. So you have to grab your test data set. Oh, that's interesting. I didn't realize you could just double click on it and see what's inside there. Huh. You grab your test data set. You need to assign a price, right? Because by default, your test data set doesn't have any price value. So we just picked randomly, every home is 100,000. And then you need to grab just the price and the ID, and then write that to a submission file. And once you have a notebook that writes something to a submission file, then you can come over here. If you click edit, you can click this little arrow. And if you scroll down, you can click submit. And clicking submit, it uses up one of your 10 daily submissions, but then it will show up on the leaderboard. And so I think you could actually already see, oh, this is skipping ahead, apologies. I should have just clicked over here. You can actually see on code, you can see, oh yes, the average error here is 251,000. And you can see, oh, the average error of this is 55,000. And this is really cool that somebody else has published their solution that gets way better than this sort of the one that I published. That's obviously, I mean, the one I published is dumb, right? But you could copy this and submit this as well. So if you're trying to climb the leaderboard, learning from other people is sort of one of the key, the key features of Kaggle for sure. Oh, it looks like we've gotten some more submissions by the since we started this stream. Okay, the last thing that I'll remind you of. Sorry, can you hear my dog scratching himself? It sounds like he has like a little bell on him. Actually, I haven't introduced y'all to Darwin this Global Hack Week. Okay, I'll introduce you to Darwin, and then we can close out and talk about prizes. Come on, bud. Yeah. Yeah, you're okay. Okay, this is my precious little angel baby. His name is Darwin. He is, I don't know if y'all can hear me when I'm turned around. He is a poodle and dachshund mix, and he is perfect, and I love him. And he doesn't love getting picked up, but he does love being cuddled. So kind of a two-edged sword. Oh, I'm glad that you could hear me. That's great. Yes, that is true. Darwin is the main character here, and we are all just supporting actors, as they say. Okay, right on. So the final thing that I will leave you on, instead, or unless there are any questions, is there are 5 ways to win a swag drop this week for this track, and they go. The first one is just by being in first place or being in second place. First place and second place, I will just do a swag drop for, right? And so right now it would be these 2 folks, but there's a lot of time before the competition ends, so you climb up there. The third way is just by submitting anything, and I will pick someone who has randomly submitted and do kind of a raffle. And then the other 2 ways are to publish code. So I will pick my favorite notebook. Right now, there's only one notebook that someone has submitted. This Random Forest one, which looks nice. I'll take a look at it later. But if you want to publish some code that you think you do something neat or interesting, then you could win for that. And the final one is for a discussion. So it looks like Loop Fruits says hot coffee is better than cold coffee no matter the season. I think I generally agree with this. I do enjoy a nice latte, but 9 times out of 10, Cortado beats it. Obviously, like great to talk about things that are related to the competition. But if you have any questions, I think last time there were actually some really great engagements where people were helping one another debug things, and I loved it. I think one of those people won. So those are the prizes that we can get. I also will talk about the Kaggle progression system because that's kind of neat. If you've stuck around this long, you kind of just we're just vibing, we're hanging out. That's why I was evolving. Yes, exactly. This is a live stream, and it will be around at least for a couple of weeks afterwards, or I think it stays on YouTube forever, which is nice. Okay, Kaggle progression system. So you may notice that some people have these sort of darker rings around their profile pictures, and some people have light blue, and some people have this tiny little, I don't know, is that like a tan? I'm colorblind, so I'm not actually sure. But this is the Kaggle progression system. And if you go to I think if you go to your profile, you can see, okay, I think you click there. You see the Kaggle progression system. So everybody has a rank in Kaggle. You are either a novice, a contributor, an expert, a master, or a grandmaster. And novice is so everybody starts as a novice, right? And then it's really relatively easy to become a contributor. You only have to do 4 things. You need to run 1 notebook or script. If you have followed along, you almost certainly have already done that. You have to make 1 competition submission, which, I mean, at least 7 of you already have submitted this competition, so that's great. You have to make 1 comment. So that's, okay, you got to go comment on something. You got to write some text. You could just write like, hey, I really like this notebook. That's a comment, right? And you need to give 1 upvote. But so very easy to become a contributor and get a little bit of a cooler profile. And then expert after that becomes a little bit more involved. But would encourage everybody to become a contributor because it is kind of a nice way to to show that you are for real and participating. Oh yeah, you just Andre, you are bad. You are sorry, not bad. It's good to see you. I'm glad you made it for the last little bit here. But yes, we are wrapping up. But you're welcome to watch the stream on your own time, and then join us tomorrow. So tomorrow, it'll be at the same time as we did it on Monday, so or an hour earlier again. The Grinch watches. Thank you for sending that. I'm so sorry that you were on the phone for that long. I feel like phone calls that take that long are very rarely fun. So, I mean, if you want to follow me, I don't really mind. You will see when I launch new competitions, which is kind of neat. But yeah, don't worry about it. But yeah, everybody can be a contributor very fast. Well, thank you so much for being here. It is a joy as always. The vibes are immaculate this Global Hack Week. Tomorrow, we will be back and we will really actually get into the heart of machine learning. So far, we have kind of been doing prep work, and a lot of machine learning is prep work. It's a lot of cleaning your data and making sure everything looks right and getting it in the right format. But then once you do all that prep work, you can really do some cool stuff. So that's what we will be back with tomorrow. I hope you were able to make it. And thank you so much for attending. And on that note, I will play us out on Kalimba again. Thanks, friends. Happy hacking.